FPSAC2014. My name is Bridget Tenner, and whether you know it or not, you've gotten hundreds of emails from me over the last couple of years. And so I'm chair of this conference, and I've worked with an amazing team of people, and they're all over the room. And I'm not going to try to name them because I would offend somebody by forgetting. But we hope you have a wonderful time here. We are so excited to have you here and to welcome you to our neck of the woods and to give you a great math conference. And so if you have any questions at any time, please try to find one of us and we'll help you out if we can. But otherwise, we hope things run smoothly and that you learn some good math and meet with some good collaborators along the way. This morning, we're going to dive right into things with maybe somewhat of a somber note, but also a bit of a celebration. So we have lost people in the last year, and one person that we've lost in particular has been certainly cited in at least half of my papers, and we're going to celebrate him a little bit today. So we're going to start off with Leclerc speaking about Alain Lascoux.
Okay, I want to thank the organizer for inviting me to give this talk in memory of Alain Lascoux. For those of you who were in Paris last year for FPSAC, you might have noticed that Alain followed many of the talks, and even he was already seriously ill. And so I think it's indeed a right place and a right moment to remember him. So when I was first asked to give this talk, I thought, what an overwhelming task. For one thing, I can say without exaggeration that without Alain I would not have become a mathematician, so my life would have been completely different. And more importantly, I think Alain has also played a very important role in defining somehow a new direction in mathematics, which is now called algebraic combinatorics, but which was not existing when he started doing mathematics. And we can see today that it is a quite successful field of mathematics now. I was checking MathSciNet, and I saw that Alain has more than 110 or 20 publications with something like 45 collaborators. So, well, it's impossible for me to give a comprehensive account of all that he did, and I have to make some choices. So, let me quote here some words of Leibniz. He writes, "It is an extremely useful thing to have knowledge of the true origins of memorable discoveries. It is not so much that thereby history may attribute to each man his own discoveries, as that the art of making discoveries should be extended by considering noteworthy examples of it." So in selecting my topics of today, I thought it would be appropriate to go back to somehow the origins of Alain's talk, or of Alain's mathematical ideas and of his discoveries. So the first thing I would like to explain, this is just a picture, but you don't need to read it exactly. This was one of the first papers of Alain, published as a note in compte rendu de l'Académie des Sciences. So maybe you can see the date, 1978, and also the field. It was not combinatorics, it was algebraic geometry. So the title, Classe de chair d'un produit tensoriel. So I want to start explaining this. It's about calculating the Chern class of a tensor product of vector bundles. So maybe before I start, I should say that algebraic geometry in the end of 60s or beginning of 70s, when Alain started his thesis, was a very dominating part of French mathematics. And due to the huge success of Grothendieck and his school in reshaping algebraic geometry, and which culminated in the proof of the Weil conjectures, one can say that algebraic geometry was like the queen of mathematics in Paris. So I don't know if this is the reason why Alain was attracted to this direction, but in any case, it turns out that his thesis advisor was first de Mazure and later Verdier, who were both a student of Grothendieck. So one can say that Alain was trained in the language of algebraic geometry, and this is where he took his first problems from. But I'm not expecting that you are trained like he was, and so I wanted to give you a very quick crash course. Is this working now? Yes. A very quick crash course on Chern classes. So first, we start with a so-called complex vector bundle of rank m on a variety x. So what does it mean? We have an algebraic variety x. Think of a curve or a surface defined by some polynomial equations. And then to each point of this curve or surface or variety, we attach a vector space of a given dimension, m. And then we look at the collection of all these vector spaces when x varies over the variety. And we call this a vector bundle. In this case, we want to have complex coefficients, so it's a complex vector bundle. So for example, think of a cylinder. You can think of this as a line bundle on a circle, right? You have a circle, and at each point of the circle you attach a line, and this makes your cylinder. You can have a different line bundle on a circle by taking a Möbius band, and again at each point we again have a line attached to it, but globally you know that the pictures are not the same. One is twisted and the other is not. So it's an important problem for algebraic topologists or algebraic geometers to construct or to classify or to understand, let's say, what are the possible vector bundles on a given variety x. And since this is difficult, they have developed lots of tools, and they have in particular constructed some sort of invariants that can be attached to vector bundles and which can allow you to understand them better. And Chern classes are part of this machinery. So Chern classes are what? So if you have now this complex vector bundle of rank m on x, then you have attached to it some elements called C1 of E, C2 of E, up to Cm of E. M is a dimension, I mean the rank of the vector bundle, and they live in the cohomology ring of the basis x. So these are some elements in the cohomology ring, or more precisely, Ck of E lives in the group H2k. And it's usual and convenient to assemble all of them, to take the sum and also to add one, and this is called the total Chern class. So I don't have time to define these Chern classes, but let me give you an example that may help you to get a feeling about it. Suppose that our variety x is the Grassmannian of k-dimensional subspaces in a complex vector space of dimension n. Right. And then, by definition, each point of the Grassmannian parameterizes a k subspace in Cn. So, by definition, at each point of the Grassmannian, you have a certain vector space of dimension k, which is naturally attached to it. And when you take all of them together, you get a natural vector bundle on x, which is called the tautological vector bundle. And now, so this tautological vector bundle is an example of vector bundle of rank k on the Grassmannian. So it will have some Chern classes which live in the cohomology ring of the Grassmannian. And probably many of you are familiar with this cohomology ring of the Grassmannian. It can be identified with a ring of symmetric polynomials modulo some vanishing of some proof functions. So in particular, it has a natural basis which is labeled by partitions or Young diagrams which sit inside a k times n rectangle, like this. So, so now the Chern classes of this tautological vector bundle are certain elements in this cohomology ring, and so they can be expanded on this natural basis labeled by Young diagrams. And in fact, up to a sign, they are labeled by the special Young diagrams, which consist of one column here. So maybe this is helpful to some of you at least. Anyway, so I don't want to define them, but I will tell you a few properties of the Chern classes which are useful in the calculation that Alain wants to make. So first of all, when you have several vector bundles, you can do some operations which generalize the operation on vector spaces, like direct sum and tensor product. So when you take two vector bundles and you take the direct sum of them, then it's known that the total Chern class will be the product of the total Chern classes of the factors. So in particular, if your complex vector bundle of rank m is a direct sum of line bundles, so of vector bundles of rank 1, then the total Chern class here will have a factorization like this. Each of the factor 1 plus xi would be then the total Chern class of a line bundle. So it turns out that in contrast with vector spaces, it is not always true that you can decompose a vector bundle as a direct sum of line bundles. Grothendieck showed that it was true for when X is a projective line, but this is a very special case. But as long as calculations with Chern classes are involved, it turns out that you can pretend, you can work as if your vector bundle was a direct sum of line bundles, and you can work with a formal factorization of the Chern class like this. And the variables which appear here are called the Chern roots of E. Right. And so the idea is that you have to calculate something. You express it in terms of its Chern roots, which may be formal variable. And then at the end of your calculation, you want to recover the things which really have a meaning, which are the Chern classes. And how do you do that? Well, they will be just the elementary symmetric polynomials in these Chern roots, just by expanding these total Chern classes here. And so you see the symmetric polynomials appearing here, and this is one of the reasons why Alain was attracted to this calculation with symmetric functions and symmetric polynomials. Okay, so now let's proceed. We take a second vector bundle of rank n, let's call it f, on the same base x, and we have also its Chern roots y. And now I can set the problem. I hope you can read it, it is down there. So the problem is, calculate the Chern classes, not of the direct sum of E and F, because I said that this follows from the axioms, but of the tensor product of E and F, and express them in terms of the Chern classes of E and of F. So this looks like a problem in algebraic geometry, but in fact, as you will see, it's just a calculation with symmetric polynomials. Indeed. Again, I'm not going to give too many details, but it is very easy for algebraic geometers to come up with an expression of the total Chern class of the tensor product of E and F in terms of these Chern roots. So it's just the product of 1 plus xi plus yj, where I and j vary through intervals 1n and 1n. So you see this expression is manifestly symmetric in the x variables, and also symmetric in the y variables. So it is possible to write it as a sum of products of symmetric function in x times a symmetric function in y. And this is precisely the calculation that Alain wanted to do. So at this point, if you don't like geometry or are not familiar with it, you can forget everything. And this is now the question: how is it possible to expand this expression and write it as a sum of symmetric functions in x's times symmetric functions in y. So, as Alain notes, if instead of this plus here, we had a multiplication sign, so we would have the product 1 plus xi times yj, then this would be quite easy. We could use the by now classical Cauchy formula. Right? We would know that this can be written as the sum of product of Schur function in x times Schur function for the dual partition in y. But this is a plus, and there is no mistake. Think of what happens when you take the product of two line bundles. It is again a line bundle, so it has to be of degree 1, not of degree 2. Right? So, how to do that? We cannot use, apparently, Cauchy formula. But in fact, yes, we can use it, and this is a nice trick of Alain. So first, let's explain how to calculate the top Chern class. So the one of maximal degree. So CMN here, because the rank of E and F are M and N. So this is obtained by taking in this product, when you expand it, you just forget about the ones, and you have this expression here. And now, what Alain does is that he pulls out all the y variables, and you are left with an expression like this. And now it starts looking like Cauchy formula, where you have 1 plus xy divided by yj. This is not a problem. We introduce the new set of variables y star, which is the list of inverses of the y's. And it's totally clear that the elementary symmetric polynomials in y star are just the elementary symmetric polynomial in y with complementary index divided by the product of variables.
You want to write y1 up to yj.
Yes, I think here I want to write yn. You're right, thank you. So you see that you can read very well. Okay, so then if we want to apply Cauchy formula to this guy here, we will have to expand it, and we will get a Schur function in x variables times Schur function in this y star. And so you have to introduce this for a given partition lambda, which sits in the rectangle n to the m. You introduce the partition lambda star given by the complements of the rows, right? I'm not doing a picture, but you see what I mean here. And then if you apply Cauchy formula to this product, and then you will have denominator coming from this, but you can multiply again by this, and then I'm skipping details, but okay, yes. You obtain the following formula for the total Chern, for the top Chern class of this tensor product.
That's y on the right, or y star?
So now it's converted to y.
Okay.
Yes. So that's why the star comes in the partition lambda. So it's really s lambda of x times s lambda star prime. So I'm using the notation of McDonald. Prime means transposition of Young diagrams, and star is this operation which I explained to you before. Okay, so this is for the top Chern class, and now what about the other ones? So again, a nice trick. If you look again at this expression for the total Chern class, you will see that it is exactly of the same kind of that one, but where xi is replaced by 1 plus xi. So it means that we can use this formula here and get that the total Chern class will be this sum, but in the first factors, s lambda will be in terms of the variable 1 plus x. So 1 plus x1, 1 plus x2, etc. I'm writing this compactly as 1 plus x. So what we are left with is to expand now this lambda, s lambda of 1 plus x in terms of s lambda of x's. And for that, you just have to go back to the definition of Schur functions as ratio of two determinants. So I'm using again the familiar notations from McDonald. The denominator here is the van der Waals determinant in terms of these new variables 1 plus x1, 1 plus xm. But when you do the differences, the 1 cancel out, and this is nothing else than the ordinary determinant. And so in the numerator, you have a determinant whose elements are powers of 1 plus xi. So you use the binomial formula, and you obtain easily the following formula here, that a lambda plus delta of these shifted variables is the sum of, for all mu contained in lambda, of the a mu plus delta times some coefficient here, which is a determinant in the binomial coefficients which appear here. So we are finished. We have obtained this result of this node of Alain, that the Chern class of the E times F can be expressed in this way, where I have defined everything, the lambda star operation and these coefficients d lambda mu. So maybe I want to say a word actually about this coefficient.
It's mu, I thought. It's mu.
Yeah. Something is wrong here. It's S mu of x. S mu of x times S lambda star. Yes, thank you. Yes, because I'm just I'm just dividing this identity by a delta. So about this coefficient d lambda mu, now you see we started from algebraic geometry, but now we end up with some nice integers here, which are given by determinants of binomial coefficients. And as Alain notes in the remarks of the note, these coefficients are positive. And this is not at all obvious from the definition of the determinant. His explanation is that he recognizes in these coefficients up to some multiples the formula is given by Schubert for the degree of the intersection of two Schubert varieties. So they have to be positive. But later on, people have developed some techniques to prove positivity of such determinants, and I'm thinking of Gesell-Vienno non-intersecting path. And this is an example in some paper on Vienno of application of these techniques to prove the positivity of the determinants. So you see how we started from a problem in algebraic geometry, and we are now much closer to combinatorics. This is a picture of Alain sitting next to Chern. This was taken in China in years 2000. I'm sorry that the quality of the picture is not very good, but okay. Now, I want to make a last comment on this first topic, and I want to use Alain's words. So, Alain has written somewhere this: algebraic geometers have introduced an adequate framework for studying symmetric polynomials. And you were thinking about so-called lambda rings, which were introduced by Grothendieck. And if you know a little bit about lambda rings, the calculations I have been explaining to you are typical of what you can do in a lambda ring. Then he proceeds and says, they have hardly used it for explicit calculation, which were not their aim. And this is true, it was not their aim. So what did they say? One rather finds in their works statements of the form, there exist universal symmetric polynomials, blah, blah, blah. So this is where Alain found somehow his inspiration to try to make these universal symmetric polynomials more concrete and to understand what was hidden behind them. So this was written in these proceedings of this famous conference which took place in Strasbourg, Combinatoire et Représentation du groupe symétrique in 76. I don't know if some of you were there, probably not so many. Here is a photo. Oh, but it's not really nice. I'm cheating a little bit. This photo is not from 76. In fact, it is from 74. This, I think, was the first Séminaire Lotharingien which took place in Oberwolfach. So this is a photo of Oberwolfach. So why I'm interested in this picture? Well, here you can see, you can recognize Alain. And the other interesting thing is that you can recognize here Schützenberger. And for me, it's the only picture I know where they are both together. So if anyone has some picture, I would be happy to get some. So if you want to recognize other names, like Jacques des Arméniens here, without beard, or Alan Morris here, Volker Strel, I mean, it's funny. Okay, so I just mentioned Schützenberger because I want to shift to the next topic, which is some joint work with Schützenberger, which is very famous, I'm sure, which is Schubert polynomials. So, Schubert polynomials. I'm going to define them quickly for you, even if many of you know these definitions. So, let's start from the ring, the polynomial ring in n variable, x1, xn, with coefficient in a commutative ring R. And we introduce the divided difference operators, this curly d, di, so there is one of them for each I between 1 and n minus 1. And it acts on the polynomial f by, you take f, you subtract the polynomial in which you switch variables xi and xi plus 1, and this becomes skew symmetric in xi and xi plus 1. So then you can divide by xi minus xi plus 1 and you get a polynomial. Fine, so it's well known that these operators, these linear operators on the ring R of x, satisfy some nice relations which are called nowadays Neal-Hecker relations. Namely, the square of di is 0, because after having applied di once to a function f, it becomes symmetric in xi and xi plus 1, and so if you apply again, then you kill the function. Then di and dj commute if I and j are far apart, and otherwise they satisfy the great relation. So it's a familiar fact then that if some operators satisfy this relation, then for every permutation W in the symmetric group Sn, you can attach more generally an operator labeled dW by just taking the product of the di1, di2, etc., dik, where I1, I2, Ik is a reduced expression for W. This will not depend, because of this relation, on the choice of reduced expression. Fine. So now let's take a second set of variables, same number of variables, y, y1 to yn, and let's take for the coefficient ring R the polynomial ring in these y variables. So there are some kind of auxiliary variables. So R of x becomes z of x and y. And now a few more notations. We denote as usual by W naught the longest permutation in Sn. And we introduce, this is a key definition, we introduce this polynomial delta xy, which is the product of all differences in xi minus yj, but actually not all of them, only those for which I plus j is smaller or equal to n. For example, xn does not appear in this, because you would have xn minus y1, and it would be already bigger than n. Okay, so now I can give you the definition by Lascoux and Schutzenberger. This appeared in a note of compte rendu in 1982. So for each permutation W, you define a certain polynomial, which is called Schubert polynomial, which you obtain by applying the divided difference operator labeled not by W, but W inverse times W naught. You apply this to this special element delta xy. And here I have to say that the divided difference operators act only on the x variables. As I said, the y's are supposed to be some coefficients. They don't see the difference, the divided differences. Right. And so the indexation is chosen in such a way that the polynomial, the Schubert polynomial SW, is homogeneous of degree the length of the permutation W. So if you take W equals W naught, then it means that you don't apply any operator, and so SW naught is just delta, which is of degree nn minus 1 over 2. So these are the so-called double Schubert polynomials because they depend on two sets of variables, and you obtain the simple, or sometimes just Schubert polynomial, by specializing the y variables to 0. These are called the simple Schubert polynomials. Oh, so why are they called Schubert polynomials and not Lascoux-Schutzenberger polynomials? This is something that, well, it's difficult to explain maybe, but the reason is that they are related with the geometry of flag varieties and of Schubert varieties in the flag varieties. So, well, before I move to that, let me show you an example for n equals 3. So this would be the polynomial delta. And then you can apply the divided difference d1, d2, d1, or d2, d1, d2. You have this familiar hexagon. So I don't think I don't have to spend too much time on this. So yes, maybe also this remark that even if the x and y variables play a different role in the definition, in the end you have this xy symmetry. That is, if you switch y and x in a Schubert polynomial SW, you get the Schubert polynomial SW inverse up to psi. Okay, so now I want to say some words about the Schubert polynomial in relation with the flag variety. So let's take the polynomial ring in the x variables only. And we define this ideal I inside Z of x, which is ideal generated by the symmetric polynomials of positive degree. And then it follows from a result of Borel that if you take the quotient ring of Z of x with respect to this ideal I, then this is isomorphic to the cohomology ring of the flag variety. And more precisely, what is the meaning of the variable x's in this identification? So we said before what is a Chern class of a vector bundle, and we mentioned also the tautological vector bundles on the Grassmannian. So in the same way, when you replace the Grassmannian by the flag variety, you have not just one but n tautological vector bundles, because at each point of the flag variety you have a flag of vector space attached to it. And so you can select the vector space of dimension k, and this gives you a tautological vector bundle of rank k. And then these tautological vector bundles are sub-bundles of each other, so you can take the quotient and you get some line bundles, and these give you some Chern classes in the cohomology ring, and these are exactly the xi's variables here in this identification. Now, why Schubert polynomials here? So, if you project the Schubert polynomials, which live in this polynomial ring, you project them in the quotient ring by the ideal, you get some elements, and it's not too difficult to check that they will give you z basis of this cohomology ring. And in fact, it turns out that this z basis will coincide with the natural basis, namely the basis of Poincaré duals of the fundamental classes of the Schubert varieties. So the flag variety has a well-known cell decomposition into Schubert cells labeled by elements of the symmetric group, and this gives rise, by taking Poincaré duals, this gives rise to a distinguished basis of the cohomology ring, and it turns out that the Schubert polynomials coincide with this basis, right? Okay. Now, yes. Now let me formulate a problem, because this is very nice, but for Alain, I think this was just a tool. He wanted to, again, to do some interesting calculation with this tool. And so here is a natural problem that you can ask yourself. On the flag variety, you have a natural vector bundle, which is the tangent vector bundle. At each point of the variety, you take the tangent space. And you can ask yourself, what is the total Chern class of this tangent bundle? So it turns out that it's not too difficult to show that in terms of the Chern classes of these line bundles xi, which I mentioned before, the total Chern class of the tangent bundle is this expression here, the product of 1 plus xi minus xj. Okay. Now, the problem is it possible to express this in terms of the natural z basis of the cohomology ring given by Schubert polynomials? So, again, you can forget about the geometric origin of this problem. You have this nice expression here in terms of x's, and you have the definition of the Schubert polynomials, which I gave you before. Can you expand this product on the basis of Schubert polynomials? And we want to work modulo the ideal I, because we want to work in the cohomology ring. So this was presented by Alain, again in a note of compte rendu, again in geometry algebraique, now in 1982. It was called Classe de Chern des variétés de drapeaux. Now it was presented by Schützenberger. Okay, and let me give you quickly an idea of the calculation. It's going to work. Yes, so you will see that in fact it is quite similar to the previous one. We introduce again these shifted variables, x1 plus 1, xn plus 1, and we call this a new set of variable x plus. And we also introduce a second set of variable y, which is just the set of x's but ordered in the opposite way, from xn plus, I'm sorry, this should be an xn, no xn plus 1 here, xn to x1. Okay, then remember, this is the expression of the total Chern class of T, and it's almost obvious that this is nothing else than delta of x plus and y with my notation of before. And so this is nothing else than the double Schubert polynomial SW0 of x plus and y. So now we are reduced to the following exercise. Given this double Schubert polynomial, can we expand it in terms of simple Schubert polynomials? And for that, before we had the Cauchy formula for symmetric functions, which was useful. And in this note, Alain finds an analog or generalization of the Cauchy formula that they continue to call. He continues to call Cauchy formula for double Schubert polynomial. I don't think Cauchy has ever seen this formula. So it's particularly nice. It says that if you have a Schubert polynomial, a double Schubert polynomial in variables a and b, then it expands in the following way. In terms of Schubert polynomials in a times Schubert polynomials in minus b. So minus b means you put minus sign for every variable. And here the sum is over all permutation u and v such that the product of divided operators du dv is dw. So it's possible to use this formula now and expand this SW0 using this formula. The other thing that you will need is to expand a Schubert polynomial in x plus in terms of Schubert polynomial in x. But you can, again, use the Cauchy formula for that. And another thing that you need is to express polynomials in y in terms of polynomials in x. And for that, you have this formula, which is not too difficult to check, modulo the ideal. The polynomial SW of minus y is going to be some Schubert polynomial in x, labeled by W0, W0. So if you use these two formulas, you can first reduce your total term class to this expression here, where we have SW of x plus, SW0, W of x, and you still have to develop this thing here. And you use again the Cauchy formula for expanding SW of x plus. It's easy to see that this is again a double Schubert polynomial with first a set of variable x and second set of variable -1, -1, -1. So you can again use Cauchy formula for that. So you end up with the following theorem by Alain, that the total term class is this expression, well, sum over all VWs. I mean, you can read it, will satisfy this condition. So I want to make a comment again about this coefficient. SV1 means you take a Schubert polynomial and you specialize all the variables to 1. So it's not difficult to see from one of the first formula of the theory of Schubert polynomial, which is called the Monk formula, that a Schubert polynomial, a simple Schubert polynomial, is a sum of monomials. So it means that this counts the number of these monomials. And there is a formula by, I think it was MacDonald who gave it first, for giving a close formula for this specialization SV of 1. But one can even, now this is really combinatorics, but one can look for combinatorial description of this monomial expansion of the Schubert polynomial. And there was quite a lot of activity on this topic in the beginning of the 90s. So there are many names who contributed to find several combinatorial descriptions of the monomial expansion of the Schubert polynomial. And I'm listing them by alphabetical order, because I don't want to go into issues of priority here. All of them did something, and you can check articles and you will see what I mean. So by specializing this combinatorial description or by using MacDonald's formula, you see that the Schubert SV of 1 are well understood. But unfortunately, and this is maybe a problem for the youngest member of the audience, unfortunately the second part here is not quite satisfactory, because we still have products of Schubert polynomials in the same set of variable x. And what we would need here is a little Richardson rule for expanding these products in terms of just single Schubert polynomials. And this doesn't exist as far as I know. So what Alain did is, in his note, he included a table which you cannot read. I'm sorry about that. But this is a table for all, I mean, he did the expansion with the help of a computer for the flag variety. I mean, this example is for the flag variety of dimension 5. And you get some very nice coefficients here for every permutations, which you can find in the note of compte rendu, and to my knowledge they are not really explained. So that would be an interesting problem. Okay, so I want to finish with Schubert polynomial by mentioning quickly the relation with degeneracy loci. We start again from our geometric situation. We have a variety X and we have two vector bundles E and F sitting on this variety X. And suppose we have a map of vector bundles H between the two vector bundles. And also that we have a flag of sub-bundles of E and the flag of quotient bundles of F like this. So what does it mean, a map of vector bundles? It means that over each fiber, if you take a point X in the variety X, you have two fibers now, one in the vector bundle E, which is a certain vector space, and another one in the second vector bundle F, which is another vector space, and you want your map H to be linear in each fiber, like this, to be a linear map from one of these vector space to the other. So, if this is the case, then you can consider the following subset of X. You give yourself some integers, let's say that they are arbitrary at this moment, R, P, Q, and you consider the set of points on X where the rank of this map, of this linear map, restricted to the sub-flag EP and to the quotient flag FQ, you want to see if this linear map has rank less than this prescription R of PQ. And this is called the degeneracy locus associated with this family of integers, and for this map here. So let me cite in a very vague way a very important result of Fulton in 1991, which says that under appropriate condition on the rank function here, which I'm not going to explain, it would take too much time, and for a generic map of vector bundle H like this, then you can look at the fundamental class of this degeneracy locus. So this is some element of the cohomology of X again. And what Fulton proves is that this is precisely, under these conditions, a Schubert polynomial in the Chern roots of E and F. A double Schubert polynomial in the Chern roots of E and F. So I cannot resist citing some words. So this was obtained by Fulton in this paper in Duke in 1991. And here is what Fulton writes. He says, since the cohomology of the flag manifold is a quotient of a ring of polynomials by an ideal generated by symmetric polynomials, a formula for Schubert varieties, as in Bernstein-Gelfand or de Mazur, is only determined up to this ideal. So when you project the Schubert polynomials in the cohomology ring, you get a basis which corresponds to the Schubert varieties, but it is defined only up to the ideal, so you could take a different representative. But then Fulton writes, Lascoux and Schützenberger introduced Schubert polynomial as a set of representatives for these classes with particularly nice properties. But of course, these nice properties is a justification for this special choice. And he concludes by saying, the present work can be seen as a complete geometric vindication of their insight. The Schubert polynomials are the only polynomials that satisfy the general degeneracy formula. Okay, I think Alain must have been very pleased when he read this. Okay, I have only 10 minutes or so left, so I should move to another topic. I will go back in time. So this is the frontispiece, the front page of Alain's thesis in '76. He liked very much engraving, and it is full of engravings like this. This is supposed to be a mathematical instrument. I don't know exactly which one. Anyway, in this thesis, you find already the definition of the practic monoid, which was further developed in work with Schützenberger, and I want to talk about it a little bit. So the practic monoid is probably much more familiar in this audience, so I can go a little faster. You start from a totally ordered set of variables, but they are non-commutative ones now. And you denote by A star the free monoid on this set of variables, namely just the collection of words that you can build with these letters, and the multiplication is concatenation. Now, the definition of the Plactic monoid, which appears in Alain's thesis, is that this is the quotient of the free monoid by the congruence relation generated by the following Knut relations. So these are some sort of commutation relations. Look at the first one. You are allowed to commute x and z as long as you have to the right a variable y which is in between x and z in the order. Or the same if y comes before the product x and z. And beware that you have here some weak inequalities and here strict inequalities. Well, this looks like a definition, artificial one, but it was motivated by combinatorial work by Robinson and Schenstedt, also by Knut. So you all know about the Robinson-Schenstedt correspondence. And it follows actually from those work that if you consider a congruence class in the free monoid, then it will contain a unique representative which is a Young tableau. And by this I mean you take a Young tableau semi-standard, yes. So you consider a Young tableau drawn maybe in the French way, and then you read it by rows from top to bottom, and you get a row, you get a reading, and this is what I mean by a Young tableau in the Plactic monoid, or in the free monoid actually. Okay. So now the multiplication on the free monoid goes down to the quotient, the Plactic monoid, and you get multiplication and associative multiplication on the classes. And since each class has a unique special representative, which is a semi-standard Young tableau, it means you have a multiplication on the set of semi-standard Young tableaux. And they have been using it, I mean, Schützenberger used this for the proof of the Littlewood-Richardson correspondence, Littlewood-Richardson rule. But here I want to mention another application, the Fultz conjecture, which says the following. Consider the Schur polynomial S lambda in some variable x and expand it on the basis of whole Littlewood polynomials. So I don't have time to explain what are whole Littlewood functions, but again I think this is familiar here. So they depend on a certain parameter q. This means that the coefficients in the expansion will be also depending on this q. And what is Fultz conjecture? Fultz noticed by calculating some example that this seems to be polynomials with positive integer coefficients. And he wanted a proof of this, and possibly a proof that would go in the following way. When q is equal to 1, the whole Littlewood function becomes a monomial function, and so this k lambda mu of q become just the Koska numbers, which count semi-standard Young tableau of shape lambda and weight mu. So he wanted to have a combinatorial statistic on the set of Young tableau of shape lambda and weight mu, such that k lambda mu of q, I mean, is given by these statistics, the sum of q to the c of t, where c of t will be these statistics. Okay? So again, the solution appeared, or this was announced in this note of compte rendu now by Lascoux and Schützenberger, second conjecture de Fultz. And it goes like this. I said that it is using the Plactic monoid, at least for the definition of the statistics. And we are in a monoid, we are not in a group. In a group we have a natural relation which is conjugacy. In a monoid we don't have inverses, so conjugacy relation becomes something like this. uv is equivalent to vu. And now what Lascoux and Schützenberger did, that they used some particular conjugacy relations to obtain these statistics. So let me be more precise. First of all, what are the conjugacy classes in the Plactic monoid? This is not a difficult question. In fact, the conjugacy classes are labeled by weight mu, and if you think of the element of the Plactic monoid as semi-standard Young tableau, then a given conjugacy class is the set of all Young tableau of weight mu and arbitrary shape. Okay, so I give this anecdote. Now, the theorem of Lascoux and Schützenberger says the following, that there is a well-defined statistics, which they call co-charge, on the set of Young tableau of weight mu, such that, so this is a normalization condition, for the unique tableau, which is a row in this conjugacy class, you put the co-charge to be 0. And then, how do you calculate the co-charge for a tableau which is not a row? And you take the first letter in the reading of the tableau, let's call it X, and the remaining letters form a word W, and you cycle this X to the last position. So you get WX, and WX now is not necessarily a tableau, but it is congruent to a Young tableau. And so you call T prime this new.
First row for you is bottom.
So let me draw a Young tableau the way they should be drawn. X is this and W is this. And so now the definition says, and you have to prove that it is well defined, but that the co-charge of T will be 1 plus the co-charge of T prime. And this defines statistics. And you have to take, if you want the charge, you have to take the complement of the co-charge with respect to the maximal value of the co-charge on a given conjugacy class. And then the theorem is that this charge statistics solves the problem. Okay, so here is just an example where we take mu to be 2 to 1. So this is a picture of all the Young tableaus of shape 2 to 1. And at the bottom I put the row tableau, which has co-charge 0. And then we look at the other tableau, and for example, start with this one. If you cycle these 3, it will come here. So this means that you have a difference of 1 here. This is a cyclage operation. Now if you cycle these 2, it will come here, but it will push the 3. So you will get, I mean, you have to use the bumping algorithm, and the 2 will push the 3 here, you get this tableau and so on. So now if you look at this by the rank, you get the co-charge, or the complementary will be the charge here. And if you want to read Koska-Ful's polynomials, for example, Koska-Ful polynomial C32, 2 to 1, you have to look at all the Young tableaus of shape 3-2. There are 2 of them, and their charges are 1 and 2, so the Koska-Ful's polynomial will be Q plus Q squared. That's the content of the theorem. So I had planned to say, I mean, something more about, yes, well, I think I have to shift things. I wanted to say that the plastic monoid was rediscovered or occurred again in the works of mathematical physicists working with quantum groups in the beginning of the 90s, and this is some description of this by Schützenberger. Yes, he says that Lascoux was organizing the expedition where we were trying to understand this quantum world in terms of the plastic monoid. So this is a picture of Lascoux, Jean-Yves Thibon here, and myself, where we were working at Jean-Yves' place in the summer vacation. So I had planned to talk about the LLT polynomial, but we switched this. I don't have time. I want to just conclude with some... yes. Well, here are the list of collaborators of Alain over the years. So you can see there are many of them. Alain was very generous with his ideas, and he sorry?
It's produced from us.
Yes, it's produced from Mathscinet with the help of François.
Which means those who check more papers in larger letters.
That's true. But this was not intended somehow, I think. I wanted to say that Alain was keen in sharing his mathematical views with many people, and I wanted to remember a few occasions when he did that. So in the end of the 70s, he went many times to Poland, and he created somehow a school of algebraic geometers using these techniques. Here you can see Piotr Pragash, who considers himself as a sort of a student of Alain Lascoux, and he has been collaborating a lot with Alain over the years. Alain also created a group in France So you probably know this phalanstère. The name comes from the utopist Fourier, which Alain was keen of. And this is a picture taken in Italy with here Pierre-André Picon, Daniel Probe, Jean Thibon, Gérard Duchamp, Jacques Desarminières, myself, and Alain Lascoux. Alain went also to China, where he taught several years in the years 2000. I think he liked it very much. So he was very generous with his ideas. He was also generous, I mean, as a person, and always involved in what is around him. So, for example, he was very active in some committees which were trying to help workers who had some professional diseases, for example, asbestos. And he was also, well, I want to show you this other thing. In the 70s, at some point, Grothendieck had some problem with the French authorities because he had accommodated a Buddhist monk which was illegal in France for some reason. And so Alain launched a petition among mathematicians to support Grothendieck and then send it around to the main newspapers in France. And there are many signatures here, like Alain Cohn and Yes, so Alain was very generous and you could say politically oriented also. Here is the front page of, I mean, this is a drawing by Alain, but it is adapted from a well-known here. No, I want to mention this because this is the front page of the last book that Alain has been working on and which is nearly completed. It's more than 400 pages and it is available from his home page. And so it contains, I mean, all the wisdom and all the nice mathematics that Alain has been working on in his life. So I strongly advise you to look at it. Yes, so that's it. Thank you.
Other questions for Bernard?
Yes.
What was the problem of algebraic geometry in the thesis that caused you to introduce the factor modeling?
Well, the thesis is divided into several chapters, and there is a big chapter 0, I think, in the mode of Grothendieck, which is about combinatorics. And there you find all kinds of things on the combinatorics of Young tableaus and also on identities between minors of a matrix. And at the end of the reminder, somehow, on Young tableaus, he just put the definition of the Plaque monoid, attributing it to Knut, actually not to himself, and he doesn't really use it later in the thesis because so I think it's mentioned there, but it's going to be used maybe after that. Yes?
Since he was doing all these computations in an era when they weren't common, was he actually very good at programming computers?
Yes.
Well, as Alain would say, in the first part of his career, he had a professional programmer who was Schützenberger. And at that time, he wasn't touching computers, but at some point, he decided to write computer program himself, and he was not at all trained in that. So, for a long time, he was using Maple, and he was also cooperating with a student of Kerber in Germany, Axel Konert, who was developing a huge computer program called Symmetrica. And so he was going frequently to Bayreuth, and together they were programming, but he was not just programming by himself. This was a hardcore computer program written in C++ maybe, And so Alain, in the end, I think he was able to program also in C++.
I would say he was an extremely good programmer, and I only know sort of the last 10 years of his life
Yeah.
when I was collaborating with him, and it was quite difficult because he would send you every day 10, 20 pages, and they were all just computer output. And by the time you'd figured out what he was trying to actually tell you, of course, it was the next day you had another 10 pages.
Yes, that's true.
But so that table would have been computed by Schützenberger then, the one that you showed us earlier?
Oh, so this one is for the flag variety of C5. So I think it could very well be that that one he calculated by hand. But what he's saying is that for higher ranks, he had to resource to the computer facilities of Bordeaux some maybe supercomputer that was existing in Bordeaux at that time.
There is an anecdote about Lascoux, that he came to La Jolla for about a month
Yes.
in 1980. And I brought him around many universities to give talks about the black monoid. And I realized at that time that there was something that he did that was really unique at that time, was to provide numbers that other people in the sky had predicted the existence, but he could actually produce them. Anyway, I brought him to MIT, where Michael Artin, I gave him a question about computing the dimensional certain variety, and his tools were just exactly what was needed to compute the dimensionless variety. And so, anyway, for these people in the stratosphere that working on homology and all that stuff that I never understood anyway. But anyway, he could provide them with numbers that they themselves could not compute. And since he was visiting MIT, Michael Artin gave him this problem of calculating the dimensionless variety. And he said, okay, I wrote down the notes, and he went back to France, and then later on he provided Michael Artin with the dimensionless variety. That was chapter 1. Chapter 2, Michael Artin gave a talk in La Jolla, and at one point he mentioned that the dimensionless variety is such and such and such, but he didn't mention Lascoux at all. And I wanted to persuade my colleagues that there was a point in algebraic combinatorics where we could provide numbers for these people who couldn't care less for them actually. But anyway, I wanted to at least show that there is something that you could do with algebraic geometry, and that was the proeminent person that it was not mentioned in this talk by Michael Artin. So I stopped at the end of the lecture, mentioned to the whole audience, I wanted him to mention Lascoux. And I told him, how did you get this number? I said, well, Lascoux gave it to me. I said, how did you do it? I wanted him to explain, his tools, He said, I don't know, he put it on the computer. I said, what do you mean that? Do you not have computers at MIT? They just would not acknowledge the fact that they had developed such amazing tools to provide these numbers that these themselves, I guess, they wanted to use them as a decoration to their talk, but they're not really anything. Just you put them on a computer.
I think it's a very good story.
Are there any other questions for the...
Well, thank you again very